I just need to put it in standard view. Okay. This says, y'all see this? Is it big enough? Identify the following solutions as either acidic or basic. And you said part B in particular. Excuse me. The value of OH minus in household ammonia. What is the value of OH minus in household ammonia? Thank you, Keegan.
Like I started it, but I wasn't sure if it was right, and I didn't want to put it in and get it wrong because I need all my points.
I know. Oh, I know. All right. How do we do this? This is KW, right? So you take the value that you're given for H3O plus, which is 3.1 times 10 to the minus 12. At least on my screen it is. And you plug that into your equation for KW. So let me just.
That's what I did. So you just divide the KW,
you do
the
1
one
times
time.
10 to the minus 14. And divide that by whatever your concentration of H3O plus is, 3.1 times 10 to the minus 12. And that will give you the concentration of OH minus.
Okay. That's what I did. I just wasn't sure if it was right because I didn't see an example problem like it. Really,
you didn't see an example problem.
Well, maybe I wasn't looking on the right page.
So many. Yeah, look. Here was
There's so many.
Problem.
There's so many of them. I'm trying to figure out which one goes to.
And that's the answer. There's so many. There's not none. Look, we did. Where was KW? I'm scrolling up on my iPad. Yeah, KW was all right here. New share to the iPad. Okay, here was example with milk. Okay, you're given the concentration of H plus, you're looking for OH minus. You're doing just the opposite here. You're given one. I always said if you know one, you can find the other. Okay, so there's KW, and you just plug in. Here you're looking for OH minus, so you plug in H plus, you divide. Oh, it is the same thing here. We have H plus in both cases. So anyways, there's that. Was there another homework problem, Danielle?
Yes, I'm trying to find it really fast.
If not, we're about to get started. This is my slides. In fact, I said I was going to post this to Blackboard, and I forgot to do that in the past 5 minutes. So really quick, I'm going to online classroom in Blackboard. Bailey's confused about the buffer diagram. Oh, we'll get to the buffer diagram. I'm going to go to lectures, and I'm just going to throw these slides up on Blackboard right now. So that you all have them. Exam 4 review slides.
I was wondering about question 21.
Okay. 2 seconds. There it is. It's a PDF. Submit. Okay, so now give it a minute. Give it, count to 10. Go into lectures on Blackboard, and at the bottom now you should see something that says exam 4 review slides, PDF. You can download that, and it's all the same slides. You said question what, Danielle? 21?
Yes, 21.
Question 21. Oh, the pH of solution is this. I was just talking about this with someone. Madison stayed on at the end of my previous review. So let me show you guys which question this is. So right here, you guys see this question? pH of a 250 milliliter sample of a buffer solution is 9.85. If 1 milliliter of 6 molar HCl is added, the pH of the resulting mixture is closest to what? So think, a buffer does what? What's the purpose of a buffer? It is to resist changes in pH. So when you're adding some strong acid, the pH might drop by a little bit because acids make pH more acidic, which is a lower pH. But it's not going to drop it by a lot, just a little bit. Okay, the point of a buffer is to maintain pH around the original pH. So 10, that's actually higher. So that can't be it. 7, that is lower than 9.85, but lower by quite a bit, lower by almost 3 whole pH integers. 0 makes no sense. It's in 1.65, it's super low. So 9.7 there is just below 9.85. So that would be what we would hope the pH would be maintained around. You're adding some acid, so you might expect pH to drop by a little, but not by a lot. Does that make sense? And then
Yes.
if you opposite, if you were to add some like strong base, like LiOH or calcium hydroxide or something, pH might raise by a little bit, but not by a lot. It should be maintained around the original pH. And we're going to look at that as our last question today when we work a buffer problem. So I'm going to stop this. Or actually, I'm just going to share over to the iPad again, and we're going to get started with these slides. Okay, here they are. So this is just a list of the big ideas from chapters 9 and 10. And just real quickly, I'm going to walk through them and remind you of a few things. Hold on in the chat. Bailey said, also, did you ever find any supplemental videos? If not, what do I look up on YouTube to find what we were doing? Bailey, I actually did look for some. The issue was that it was either like a 30-minute long video and portions of the video were like portions that were unrelated to things we talked about. Maybe a small portion of the video was actually applicable, but I didn't find one that just walked through a good example. So how about this? Let's work one today and let me know how you feel after we work a whole buffer problem all the way through, all 3 parts. And hopefully you'll feel better about that. If not, we can then discuss maybe some supplemental resources. Okay, big ideas. Chapter 9, it was all about solutions. We talked about solubility, defining solubility, saturated solutions. We said solubility has units of gram per 100 ml. And you don't divide by the 100. To decide if you are going to get a solution, we use this principle of like dissolves like. Also, I'm going to move at a decent pace. So if I'm going too fast, this is very informal. Stop me, slow me down, holler at me in the chat. Like dissolves like. So that's the first problem we're going to work is a like dissolves like. How do we know if certain solutes will dissolve in certain solvents? Okay. We also looked at increasing or decreasing. How do you manipulate solubility? If you have a solution where you have a solute that's a solid, so a solid in a liquid versus a gas in a liquid. Okay, for solids, the trend was this. If you increase temp, you increase solubility. Opposite for gases. A gas dissolves in a liquid such as like a Coke. If you increase temp, you decrease solubility. We use those solubility charts where you saw the trend, the data lines with a positive slope for solids and a negative slope for gases. We looked at Henry's law. I'm going to zoom in. I'll be right back, which was C1 over P1 equals C2 over P2. We're going to work a Henry's law problem in just a little bit. You'll be given 3 of the 4 pieces. You solve for the 4th. If you're trying to solve for pressure, you got to flip the whole equation, okay? You don't want to solve for something on the bottom. We looked at units of concentration, mass volume percent, which is grams of solute per milliliter of solution, grams of solute per milliliter. Sorry, my handwriting is all over the place today. Not making it any better. milliliter of solution, and it's times 100. Molarity is moles of solute divided by liters of solution. And you can actually convert between these two. If I give you a percent and I say, what's the molarity? We're going to work a problem like that. Convert grams to moles, then you convert the milliliters to liters, and then you solve for molarity. Okay, molarity as a conversion factor. There's several problems on your chapter 10 homework like this, and there will be one on the exam that involves this, so we'll work one of these. Anytime you have a titration problem, you're using molarity as a conversion factor. Dilutions, we had an equation for that. M1V1 equals M2V2. Now, some of these equations, not all of them, but some are on your exam for resources page. If you click into the exam folder on Blackboard, that's already in the exam folder for you. So you can click on that resources page and see what I put on there. I put a few equations at the top, like equations for pH or Ka, but I didn't put everything. I just put some. And then electrolytes. We talked about strong, weak, and non-electrolytes. We're not actually going to work a problem like this on the review today, but we had a quick review from the chapter 9 slides where I give you 3 equations. I say, okay, which one's a strong, which one's a weak, and which one's a non-electrolyte. We even did a poll question on that. Remember, things that do not make ions, they're not electrolytes. Okay, things that completely disassociate into ions are strong electrolytes. Things that weakly disassociate would be weak electrolytes, and you get a double arrow. Osmosis, make sure you know how osmosis works. It's based on a gradient. And how does solvent move along that gradient? We wrote that out on our osmosis slide. Okay, solvent always moves from an area of low concentration towards an area of high concentration to dilute that high concentration. Okay. And then words like isotonic, hyper, and hypotonic. Be familiar with those and what they mean. If I give you different solutions or I had you calculate osmolarity of different solutions, I'd want you to tell me, if one's isotonic or hypo or hyper. And what is osmolarity, by the way? If we're going to calculate it, we're going to work a problem like this today. It's moles of particles per liter of solution. Okay, it looks a whole lot like molarity, but instead of moles of the compound, we're looking at moles of particles. So you got to ask yourself, will my compound break apart into any particles, ions? If it won't, then your molarity is your osmolarity. If it does, you just multiply your molarity by the number of particles you would get in solution. If it's 3 ions or 4 ions or 2, you just multiply it by the number of particles that you would get. Okay. All right, it's chapter 9. Chapter 10, big topics. Identifying, if I give you a reaction and you got to tell me what's the acid and what's the base. We practiced that. Remember, those are just on the reactant side. Identifying also conjugate acid-base pairs. The conjugates are always on the product side. And remember, if it's an acid on the reactant side, it's the conjugate base on the product side. They flip. Okay, acid-base strength. You have a whole table of those things. And we have strong acids, weak acids, strong bases, weak bases, but we have Ka for weak acids, okay? Because we get an equilibrium, and you can solve for the pH using Ka of a weak acid. If you know the initial concentration of the acid. Kw, we just looked at that a minute ago, but we'll remember Kw equals concentration of H plus or H3O plus times the concentration of H minus. So if you have the concentration of one ion, or if I give you the pH, you could always calculate the concentration of H plus and then calculate the concentration of H minus, or you can use this equation that's where pH plus POH equals 14. And you can always subtract one off the other and solve for pH or POH that way. pH though, okay, if you're not dealing with a buffer, like you're just dealing with a solution that has an acid in it or a base or whatever, equals the negative log of the concentration of H plus. All right, now the moment you have a buffer, you have a different equation. It's called the Henderson-Hasselbalch equation. By the way, unfortunately, sadly, still crying on the inside about this. We did not get to the blood buffer system. If you have a buffer, the equation is different. It's the Henderson-Hasselbalch equation, which is that pH equals pKa plus the log of concentration of the conjugate base divided by the concentration of the weak acid. And we're going to do a buffer problem at the end of today, so stick around, do a 3-part problem. Lastly, we did a whole lab on titrations, so you better know how to work a titration problem. Remember how you had to calculate the molarity of acetic acid from the vinegar titration? Know how to calculate using molarity as a conversion factor in a mole to mole ratio. All right, those are the big ideas. Let's start working some problems. Which compounds dissolve in the following? Oh, sorry, what? Go back up. All right, which compounds dissolve in the following liquids? And it took me forever to answer this in the first session this morning because I realized I realized that I wanted an electronegativity chart to solve this. So this is like dissolves like. So let's look at our solvent here. Our solvent is methanol. Okay, it says in methanol. So the methanol is the solvent. So we got CH3, and then we got OH. Okay, so is this polar or non-polar? What do you guys think? Keegan says polar, he's correct. We got dipoles right here. Okay, now remember this is going to be a geometry that's bent, so these dipoles don't cancel. Okay, it'd be more like this, COH. So the dipoles are pointing both towards the oxygen, same direction. And so this is polar. So now we just got to decide which one, CSE2 or OCl2, which one's polar. All right, and if I'm looking at the electronegativity chart, the difference between carbon and Se has electronegativity of 2.4, carbon has an electronegativity of 2.5. So none of those bonds are going to be polar. No matter how you draw the molecule, none of the bonds are polar. So this is nonpolar. So if I'm a betting person, I just circle OCl2 and I move on. Okay, I don't waste time on the exam calculating every little thing because I already know that one's nonpolar. Now, looking at electronegativity for OCl2, which is going to look a whole lot like a water molecule, it's bent. The difference, oxygen is 3.5 and Cl is 3.0. So the difference there is 0.5. That is polar. So we got dipoles there, both pointing towards oxygen. This is polar. So yep, that one will dissolve in methanol. Okay, carbon tetrachloride or ammonia in water. First off, you don't even have to draw water out. Is water polar or nonpolar? If you learned anything in this class, hopefully you learned that water is polar. So carbon tetrachloride or NH3, which one is polar? You want me to draw them out? Thank you, Keegan. NH3 is polar. Whoops. Carbon tetrachloride is CH4. Anytime I see just carbons and hydrogens, I should know that's not a polar molecule. I don't care if it's C2H8, C2H6, C10H1000, okay? Anything with just carbons and hydrogens is a nonpolar molecule. Okay? So NH3 will dissolve in water. And then we got LiOH. This is ionic. I got Li plus and OH minus. So remember, polar and ionic compounds dissolve in solvents that are polar. Nonpolar compounds dissolve in solvents that are nonpolar. Methane, CH4. Oh, why did nobody corrected me. It's not CH4. This is CCl4. So you actually might want to look at carbon tetrachloride. Between carbon and chlorine. So maybe we did want to draw this out. Sorry, I was going too fast. It looks like this. The electronegativity difference between carbon and chlorine. I'm seeing in the chat. It is a polar bond. It's a difference of 0.5, but it's symmetrical, as everybody's saying. So all these dipoles that you could draw in up and down as well, they all cancel. All right. So the molecule's symmetrical, so it's still nonpolar overall. but not for the reason I mentioned earlier, which is right here. So this one is ionic and this one's nonpolar. So which one will dissolve in C3H8O? So you look something like this. And then you got hydrogens all over these carbons. So you think this is polar or nonpolar? We will have dipoles right here, and they don't cancel because they're pointing the same direction. So polar, so LiOH, that one will dissolve. Ionic and polar solutes dissolve in polar solvents. Okay, questions on that one? How do you guys feel about functional groups, by the way? Anybody watch the functional group video?
I forgot to watch it.
Okay, please watch it. That's 10 points on your exam. And I walk through some practice problems at the end. And I think I'm gonna do one problem at the end that I didn't do this morning, and I'll work a functional group example problem from the textbook. Y'all don't let me forget to do that. Somebody remind me at the end, hey, work a functional group problem. Okay, Henry's law. Here's this. So blah, 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 blah. Calculate the solubility of oxygen in water at 25 degrees and a partial pressure of, so here's my first pressure given, but I don't know if that's necessarily, I'm not going to necessarily call that P1 just yet. The solubility of oxygen in water is, here's C1, here's P1. Okay, that's associated pressure. So it's given us an original solubility, 0.00414 grams per 100 ml. And then it's given us the associated pressure, 760 torr. You can't see it? Why is it frozen? Yeah, y'all are still looking at the, let me stop share and reshare. I'm telling you, we are having all kinds of technical things today. Can you hear me now? Okay. So I was saying on the exam, it's not going to tell you, oh, this is Henry's law. You're going to have to understand that it's Henry's law from reading the problem. Okay. So it's giving you a solubility right here and a pressure, and it's asking what is the new solubility, so C2, at this new pressure, P2. So I'm trying to solve for C2. So I'm going to take my equation, and I'm going to multiply both sides by P2 because I'm trying to isolate C2. So P2 times C1 over P1 equals C2. Okay, so now we just plug everything in. So 1150. By the way, I gave you this relationship. Here's ATM, but disclaimer, you can work the whole problem with units of torr. So forget converting. I'm just going to work it all torr. Times C1 is 0.00414 grams per 100 ml divided by 760 torr. And you should get, what do you guys get? I got 0.00626. Is that what y'all got? Did I do that right? Yeah, okay. And what are the units there? Gram per 100 ml. That's my new solubility. Now, if it said, if it wanted you to solve for pressure, what do you need to do? You need to flip the whole equation. You can't solve for 1 over pressure. You want to solve for pressure in the numerator, not in the denominator. Okay. Next thing, we're going to work a problem where we're using molarity as a conversion factor. Again, the heading of the problem is not going to say, here you need to use molarity as a conversion factor. You're going to have to figure out by reading the problem the steps that you need to take. So anytime you're given a volume and a concentration of one particular reactant or product, and you're asked for information, here we're asked how many grams of another reactant or product in the equation. It is a 3-step problem. Okay. So here's the yeah, these are not easy. Okay, here's the steps. Start with the component that you have all the information on, like a volume and a molarity, or grams and a molar mass. Start with that. Okay, we're going to call this substance A. We're going to call NaHCO3 substance B. And you have to have a balanced chemical reaction because we need a mole ratio. So we're going to start with the volume. That's not how you spell volume. Volume of substance A, which is the 450 milliliters. We're going to start there, and we're going to convert to moles of substance A. So step number 1 is we're going to plug in the molarity, and we're going to convert from volume to moles, because that's what molarity is. It's moles per liter. We can convert between moles and volume using molarity. Step number 2, you're going to convert from moles of substance A to moles of substance B, and we always use a mole ratio. That's why I need the balance reaction for this, okay? And then here we're asked how many grams of sodium bicarbonate. So we're going to convert from moles of sodium bicarbonate to grams of sodium bicarbonate. So how do we go from moles to grams? What do we use? Anytime you convert between grams and moles or moles and grams, you use, thank you, Brooklyn, molar mass. Okay. So step number 1, start with the volume, 450 milliliters, and this is H2SO4. And I want to use molarity, okay, which is mole per liter. So if I'm going to use molarity to convert from volume to moles, I need to have my volume in liters. So I'm just going to convert this to liters. So that milliliters cancel. Whoops. Now I'm going to plug in, this is step number 1. So I had a pre-step there. My pre-step was to get it in liters. Step number 1, plug in molarity, which is, I'm going to zoom in for a second. It's 0.5 moles per liter. I always encourage you to rewrite it like this. Anytime you see capital M for molarity, you know that's 0.5 or whatever the number is. It could be 0.25, it could be 0.025, but it's moles per liter. So you need to see it that way so you know how to write it. It's 0.5 moles on top per 1 liter on the bottom, because we're trying to cancel liters and convert to moles. So we just use molarity to convert from volume to moles. Okay, now here comes step number 2. We're going to use the mole ratio. What is our mole ratio? Well, we're just going to look at H2SO4 and sodium bicarbonate. So it's a 1 to 2. So I'm trying to cancel moles of H2SO4. That's what I have on top right now. So for every 1 mole, it's 2 moles NaHCO3. And moles of H2SO4 cancel. Okay, the last step was to use the molar mass of sodium bicarbonate. I looked it up earlier. It's 84 point something. 84.007. Okay, so the molar mass for HNaHCO3 is 84.007 gram per mole. So I'm going to erase my little diagram so I can keep going. I'm plugging in the molar mass here. This is step 3. I want moles to cancel because my question is how many grams. So for every 1 mole of Na, I don't know what happened. I think I accidentally hit that button on the side. NaHCO3. It's 84.007 grams. And then we see moles sodium bicarbonate cancel. So everything cancels except for grams of sodium bicarbonate. Now we plug it all in the calculator. 450 divided by 1,000 times 0.5 times 2 times 84. Keegan, Brooklyn, okay, good. Everybody, 37.880 grams. Okay. Now, what if I, instead of asking for how many grams of sodium bicarbonate, what if I gave you all the same information, but then I said, you already have a solution of sodium bicarbonate and it's 0.25 molar. How many milliliters of that solution would you need to dump on the floor to neutralize the acid? Same idea there, but for step 3 here, instead of using a molar mass like we did, you would just use the molarity of sodium bicarbonate to convert back to volume. Does that make sense? Still a three-part problem. Okay, we did an example of this in lecture. I'm going to show you the example that I'm thinking of. After we talked about Henry's law and concentration, we looked at molarity as a conversion factor. Right here, we worked this problem. Okay, where I gave you a volume and let me erase right here. I gave you a volume and a concentration for HCl, and then I gave you a concentration for sodium or calcium carbonate. And my question was how many milliliters? So there, 3-part problem. See my 1, 2, 3. But here we plugged in a molarity instead of a molar mass. Same exact thing. Always the mole ratio is your middle step. And then there we are trying to convert back to a volume, not grams, like we just did. So there we just, step 3 was plugging in a molarity, not a molar mass. Converting back from moles to liters instead of to grams. Now does that make sense? Okay. Okay. Moving on. Dilution problem. You have concentrated 12 molar HCl. And the question is right here. How many milliliters of 0.5 molar HCl can be made from 25 milliliters of 12 molar HCl? Somebody tell me what to do. Unmute yourself.
Isn't it just M1, V1, M2, V2?
It is. So what do I need to plug in? What's my M1 and V1?
25 milliliters and 12 molar molarity.
Perfect. So that means it's my M2. So I'm solving for V2. So M1 V1 equals M2 V2. So divide both sides by M2. So M1 V1 over M2 equals V2. Okay. Now you just plug everything in. 12 molar times 25 milliliter. And it doesn't matter if you write the molarity of the volume first. What matters is that you're multiplying them. Divided by 0.5. Okay. So I think last time we got 600 milliliters when you plug all that in. Good. So because you have milliliters right here, your units are going to be in milliliters. If I said how many liters, you just convert it to liters in the end. Okay. Questions on that one? Okay. All right, now let's get to some hard stuff. Some more hard stuff. Osmolarity. Know how to do this. So calculate the osmolarity. You're given 3 solutions here. Remember, we actually have, they tell us the molarity of all the different compounds. So for each compound, you look at how many ions or particles would this dissolve into, and then you just multiply your molarity by that number. So let's zoom in on the first one. Calcium hypophosphate, CaHPO4. Calcium is a cation with a 2 plus. HPO4 is a -2. If you look at your polyatomic ion chart, it's on there. So this is no magic here. You just look at your polyatomic ion chart. And so I'm going to get, and you could look at the subscripts, right? Knowing that this is a polyatomic, I just get one of these and one of those. So total, I get 2 particles. So I'm just going to say 0.2 molar times 2, because I get 2 particles each. I'm going to get a total osmolarity of 0.4 osmoles. Okay, that's moles of particles per liter. For every, remember that 0.2 molar is 0.2 moles of the compound per liter. And I'm going to get 2 particles. So if I have 0.2 moles of the compound per liter, I'll get 0.4 moles of particles per liter, which is the 0.4 osmolarity. Okay, that's the easy one. 6 and 7 are harder because look, I got 0.1 molar glucose and I have another thing, and it wants to know the osmolarity total. So I got to calculate 2 different things and then add them up. So let's look at number 6 right down here. Glucose. How many particles are we going to get? How many ions will it dissolve into or break up into?
Does it not break up into anything because it's, I don't forget what you said.
Direct biological molecules such as glucose, fructose, insulin, whatever, do not break up in ions. So you just multiply the molarity there by 1, right? Because I'm just going to get 1 particle, glucose particles. That's it. So if I have 0.1 molar glucose, that is equal to 0.1 osmoles. Okay, so that's part of it, but we have another compound here. I have 0.2 molar NaHCO3. How many particles would I get from sodium bicarbonate? Yep, Keegan says 2. I'm going to get Na plus, that's 1. I'll get HCO3 minus, that's another 1. So total 2. So say, okay, times 2. Now I add up 0.1 plus 0.4. Total, I get 0.5 in that whole solution. I got glucose, and I got sodium particles, and I got bicarbonate particles all floating around. Number 7, calculate the osmolarity of 0.3 molar fructose and 0.2 molar magnesium chloride. I'm going to give you all a minute to do this one. I want y'all to work this out. Don't watch me do it. I want you to try it. See if it makes sense in your head, and then I want y'all to tell me what answers you get. This is total. So calculate the osmolarity for the fructose portion and the magnesium chloride portion and add them together. Keegan said 0.7. Brooklyn said 0.7. Everybody says 0.7. Emily says I got 0.9. Abby says 0.9. Uh-oh. So how do we know? 0.7 or 0.9? Well, fructose is like glucose. So the osmolarity there is just equal to the molarity. So if I have 0.3 molar, we know that's times 1 because you get 1 particle. That's fructose particles. So that's going to be 0.3 osmoles. All right, so it must be some difference here with the magnesium chloride for the reason we're getting different answers. If I have 0.2 molar MgCl2, I'm going to get Mg2 plus particles. So that's 1 particle there. And I'm going to get 2 Cl minus, and that's 2 particles. So total, when this thing dissolves, I'll get, yes, I have 1 cation and 1 kind of anion, but I'm going to get 2 chlorides every single time. So it'll look like this. MgCl2 in water becomes this. Mg2 plus, Cl minus, Cl minus. I'll get 3 particles every time this thing dissolves. You see that? Total, you can add up the subscripts if you're ever like confused on how to do it. You just got to know what's a polyatomic and what's not. Add up your subscripts. I have a understood 1 there and a 2 for chloride. So 1 plus 2 is total 3 particles. Okay, so what I got to do is I have to multiply my molarity times 3, which means I get 0.6 osmoles. Okay, so it only works when it is not a polyatomic. Keegan, it works even when you do have polyatomics. Okay, we had polyatomics right here with sodium bicarb. I just have to understand that I have the 3 here doesn't mean I have so like on sodium bicarbonate, I had NaHCO3. This 3 doesn't mean I get 3 polyatomics. It just means I got 1 bicarb and I got 1 sodium. Okay, so 1 and 1 means I get 2 particles there. And that's why we multiplied it by 2 here. But here I'm looking at a compound where I'm going to get 3 particles every time it dissolves. So that's why we got 0.6 plus 0.3. Yes, it is 0.9 osmoles. Okay, so let me ask another, just as to drive this home. What if you have AlCl3? How many particles do you get when that dissolves? Now y'all are getting it. What if you have Al2SO4 How many particles do you get when that dissolves? There, y'all got it now, 5, okay? And then you would multiply your molarity by that number of particles. Okay, so questions on calculating osmolarity? Now, can y'all tell me, I actually didn't do this morning, considering, so you got 0.4 for the first one, I got 0.5 for the second one, and I got 0.9 for the last one. Do I have any solutions here that are isotonic? Are any of these solutions isotonic? Y'all remember what that means? Are you saying no, you don't have any solutions that are isotonic, or no, you don't remember what that means? Okay, Bailey said no, and she's right. Isotonic means same osmolarity. I have no solutions here that are isotonic. Can you tell me which one is hypertonic compared to the other 2? Which solution is hypertonic compared to the other 2? Solution 5, yep. Yes, solution 7, which is what Keegan said, 0.9. Okay, that one's hypertonic. The one that would be hypotonic compared to the other two is number 5. It has the lowest osmolarity. How do you know? Hyper and hypo. Okay, so hyper means it's stronger than or more than. So you'd pick the one with the highest osmolarity is always hypertonic compared to solutions with lower osmolarity. Solutions with a lower osmolarity are always hypotonic compared to solutions with a higher osmolarity. Hypo is the lowest osmolarity, hyper, highest osmolarity. All right, I was telling the morning people I worked this problem last Thursday and it's already recorded and posted to Blackboard. If you go into the supplemental videos folder, I worked this problem step by step. We did it last Thursday in our study session, the Listerine problem from the book. It's a great problem, so go catch that part of the video. So I'm going to skip over it for now. Okay, this is a really, really good one. Converting between units of concentration, between a mass volume percent and molarity. So it says the concentration of glucose in blood is approximately 90 milligram per 100 ml. What is the mass volume percent concentration, and then what is the molarity? Okay, so we're solving for 1, what is the mass volume percent? Number 2, what is the molarity, which is moles per liter. Mass volume percent is grams solute, which is, I'm just actually going to erase this here. It's grams of glucose because that's our solute per milliliter of solution, which is our blood for this one, times 100. So just plug things in, right? Says your concentration for glucose is 90 milligrams. That is the, well, solute. And 100 milliliters, this is the solvent. Or sorry, blood is actually the solution. So solute and solution. So we plug the 90 milligrams in on top, 100 ml on bottom. But we can't just plug in 90 milligrams. We got to convert it to grams. 90 milligrams for every 1,000 milligrams, that's 1 gram. So it should be 0.09 grams. That's what we plug in on top. So mass volume percent is going to be equal to 0.09 grams. This is glucose we're talking about. We're dividing this by 100. We don't have to convert anything about the volume of our solution. It's already in milliliters times 100. And by George, what happens? The hundreds cancel. So our percent is 0.09%. Okay. Now, how do we convert this to moles per liter? I'm going to zoom in for a second. We have grams of glucose, and we're trying to convert this to moles of glucose. We have milliliters of solution, and we're trying to convert this to liters of solution. Okay, that's molarity, mole per liter, right? So how do we convert from grams to moles? Plug my computer out. Yep, Keegan, molar mass. Okay, so the molar mass of glucose, when you teach this course a lot, you memorize it actually. It's 180.156 gram per mole. So why don't y'all go ahead, I gotta plug my computer up, start trying to convert this to moles. Anybody get number moles? So you should have done 0.09 0.09 grams for every 180.156 grams. That's 1 mole of glucose. And then milliliters, we got 100 milliliters. And for every 1,000 milliliters, that's 1 liter. So that is equal to 0.1 liters. How many moles is it? 5 times 10 to the minus 4 moles. So you just do that divided by 0.1, which means you get 5 times 10 to the minus 3 molar. So my molarity is 5 times 10 to the minus 3 moles per liter. I like this problem a whole lot because you really have to understand what you're doing with units of concentration to answer all of this. You've got to understand mass volume percent and molarity and how they relate, how to go back and forth between the two. All right. Here's some pH stuff. So we got a pH problem and then a buffer problem. And then I'll do a functional group problem. So 3 more and then that's it. We worked this morning, this problem 10.54, like all the way around this long way, and we did way too much work for it. And then I realized, what am I doing? It was very much more simple than what I was trying to do. This one, it's deceiving though. The reason this problem is tricky is because it's kind of deceiving. It even deceived me. It says calculate the concentration of H3O+. All right. For if you have a 0.1 molar solution of acetic acid, which is a weak acid because it's right here on our Ka table. So what's happening is any weak acid, you get this double arrow because it's disassociating in H+. That's my H3O+, right? H+, H3O interchangeable. And CH3COO-. Okay. So there's my dissociation reaction. And I have 0.1 molar of this weak acid. And I'm trying to calculate, it says calculate the concentration of H3O+ for a 0.1 molar solution from the problem 10.5, the previous problem. Well, we don't have the previous problem, so I just put this piece of information right here. If you had done the previous problem, it asks you to calculate pH, and the pH is 2.88. What is the percent of the weak acid that is disassociated? Okay, so I'm actually going to move this down here. What percent is disassociated? Okay, so here's what we know. We're told that we have 0.1 molar of our acid initially. That represents the whole concentration of the acid. Before any of it disassociates, it's a 0.1 molar solution. But then some of it disassociates. So we lose some of this and we make some of this and some of this. Okay, we don't know how much though, right? So how are we going to solve for any kind of percent? Like, how do we know how much what the percent is? Well, percent is always part over whole times 100 to turn that decimal into a percent. So the portion that disassociated is going to be equal to the concentration of this, and that's what it's telling us to solve for. Calculate that. And the whole amount is right here. This is whole. The whole amount of the acid. The portion that disassociated is going to be equal to the concentration of our product. So this is the part. So we can calculate H+, then we can divide it by 0.1 and calculate a percent. Okay. Now, if our pH of this, we know the pH. If the pH is 2.88, can we get the concentration of H+ from pH? How can we do that? How can we get the concentration of H+ from pH? Anybody remember how we do that? How do you get the concentration of H+ from pH? Bailey said antilog. So what is our equation for pH? pH equals negative log of the concentration of H+, which is what we're after. We want that. So we just got to undo it. Yep, so it's 10 to the negative pH, right? That is always equal to the concentration of H+. So it's really easy here. All we do, come over here, we just do 10 to the negative 2.88. And you should get, what do you get, 0.0013? I did not do this in my head. This is just what I remember from this morning. Is that right? Somebody check me. I think that's what it is. I don't see anybody okay. So now what do we do? That is the part, and this 0.1 is the whole. So we're just going to do that division times 100. So 0.0013 divided by 0.1 times 100. You get 1.3%. Right around that. Okay. Lord have mercy, I was trying to use Ka and calculate for x squared and all that, which you need to know how to do because we did a problem like that. Remember in lecture when we calculated the pH for a weak acid solution? Anytime you are asked to calculate pH of a weak acid, you have to use the Ka and solve for x squared. We worked a whole problem like that in lecture. It was right down here after we talked about pH. An antilog. There, we did this problem where I said, here's a weak acid, here's the Ka value, here's the initial concentration. What is the pH? These are hard problems. Calculating pH for a strong acid is easy. You just do negative log of the concentration. But calculating pH for a weak acid is hard. You got to use the equation for Ka, okay, your expression for Ka, and you plug in x for both of these things, and then you just solve for x squared. That's your concentration of H plus, and the last thing you do is the negative log of that. But there's lots of steps. It's way more complicated than just if you have a strong acid. Okay? Too much algebra. Get used to algebra. If you're going into a health profession, you're going to be using algebra. All right, algebra never goes away. Okay. I would even say it's like catching and throwing. Those are just necessary skills in life, okay? Algebra is a necessary skill in life. I'm dropping out. Don't do that. You're a week away. Okay, which of the following buffer systems? Okay, this question I realized is not exactly what I wanted it to ask, so ignore that. We didn't actually get to talk about that. We're just going to consider, let's pretend we have a buffer, whatever, Keegan. We have a buffer like solution A. Okay, we have 0.08 molar H2PO4. We have 0.12 molar HPO4 2 minus. And I want to know that we're going to do a 3-part buffer problem. So we're going to do a part 1, then we're going to do a part 2, then we're going to do a part 3. Okay. And here's our buffer. We have to use Henderson-Hasselbalch. Anytime you have a buffer, you've got to use, if you're calculating anything about pH, yeah, this is ice chart. pH equals pKa plus the log of the concentration of A minus over HA, which is the conjugate base on top, always weak acid on bottom. Okay, this equation's on your resources page for exam 4, but you only use it for buffers. So, number 1, what is the pH for the buffer in part A? That's like a question. That's the first question. What's the pH? We're just going to plug everything into Henderson-Hasselbalch. And we need pKa though. That's the only part we don't have. We're given the concentrations 0.08 and 0.12. We're literally just going to plug those into the log term, but we don't have pKa. So I have a table of Ka values, and we need the Ka for the weak acid. So here were your components, H2PO4 minus and HPO4 minus 2. Which one's the weak acid? Which one's the conjugate base? Answer only my first question. Which one's the weak acid? Keegan says HPO4 as the weak acid. You need to pick the one here that has more hydrogens. Okay, the acid gives away the hydrogen. So this one is your weak acid. And then when it gives away a hydrogen, what's left over is the conjugate base. Acids donate, they're proton donors. They give a hydrogen away. All right, if this gives a hydrogen away, if that gives a hydrogen away, then you're left with H plus and PO4 minus 3. Well, we don't have that anywhere in our buffer. Okay, so this one is our weak acid. So that is this right here, because we need to decide, do we need this number or that number? 2.2. We don't need the 2.2. We need the 6.2 times 10 to the minus 8. So pKa is the negative log of Ka. So we're just going to do pKa equals negative log of 6.2 times 10 to the minus 8. I'm just grabbing that number off the table. And I think I remember from this morning, it was 7.21 when you do that. Okay, now plug everything. We're not done. That's not the answer. The question is what's the pH? We haven't solved for pH yet. So now we're going to plug everything into Henderson-Hasselbalch, which says that pH equals pKa, which we now know is 7.21 plus log of concentration of conjugate base on top. So that's this one, 0.12 molar divided by weak acid, 0.08 molar. I know we're over time. I'm going to finish this and work a functional group problem, then we'll be done. So 7.21 plus the log, not minus the log, plus the log here. 0.12 divided by 0.08. And I get pH equals 7.39. Okay, questions on that? All right, next problem. Here, parts 2 and 3, you're examining how does a buffer respond when you add some of a strong acid or a strong base. Okay, it does not matter which one you look at first. So we'll just look at what happens when we add a strong acid. And the next part, we'll look at what happens when you add a strong base. Okay. So when you add a strong acid, you expect pH to drop by just a little, but not much. When you add a strong base, you expect pH to raise by just a little, but not much. So what if we add 0. I'm going to make up numbers here. 0.18 mole of HNO3, that's a strong acid. And let's say that you have 1.2 liters of buffer. All right. The first thing you got to do always is calculate molarity. What is molarity for the acid HNO3? That's moles per liter. So I'm going to plug in my 0.018 moles divided by my 1.2 liters. And I get 0.015 molar. I've got to have units of molarity. Then I set up my ICE chart. And I'm going to calculate how my buffer components change, their concentrations, how they change. H2PO4 minus HPO4 minus 2. So initially, I just plug in the concentrations that part A tells me, 0.08 and 0.12. Now, I know they're going to change by this much, but which one's going to go up and which one's going to go down? because one of these buffer components is going to get used up to neutralize this acid. And in the process, we're going to make more of the other component. Okay, so let's examine that. Buffer, I'm going to use a buffer diagram. This is actually on the homework, and we worked a problem earlier just like it or similar to it. So buffer diagram. We have HPO4, H2PO4 minus, and that's in equilibrium with HPO4 minus 2. This is the weak acid. This is the conjugate base. HPO4 is used, Bailey. That's exactly right. The conjugate base is going to be used to neutralize this acid here. So this is going to go down, and this one's going to go up. Because when you add a strong acid such as HNO3, it disassociates to H plus, NO3 minus. This guy, H plus, could threaten to lower our pH, but the buffer says nope. So this guy, the conjugate base, is going to sweep it up, and what happens? You make more of your weak acid in the process. So that's why we say the concentration of this goes down, it gets used up, and then just inherently we make more weak acid. These are the arrows that are important for figuring out, okay, I'm going to make more of this, I'm going to use up some of that. That's telling me how I write my plus and minus in. So then we just write the number, 0.015 on both columns. And it's units of molarity, not moles. Okay, then we just add and subtract.
Can you explain again really fast how you knew that it was the H2PO4, well, the one that was getting used up? How can you explain that again?
Yes, Danielle. This is my conjugate base, right?
Mhm.
Bases neutralize acids. I'm adding an acid down here. Bases neutralize acids. So that's why I said this one's going to get used up, because it's the one that's going to neutralize the acid. So if I'm using it up, the concentration will decrease in the solution in the buffer. Acids don't neutralize acids. This is my weak acid. Acids are reserved to neutralize bases. So we'll look at that in just a minute. My motto here is when you add acid, okay, we're adding an acid, you add to the acid column. This is the weak acid column. So if you add acid, then you add to the acid column. That's my motto. All right, so what does this equal? 0.23? No. I'm way off. 0.08 plus 0.015 would be 0.095. I don't know what I was thinking. And then subtracting, so we get 0.105. And now we just plug these. These are what we plug into Henderson-Haas block. So pH equals pKa 7.21. That never changes through all three parts of a buffer problem. Stays the same. What does change are your concentrations that you plug into the log term. 0.105 goes on top. Remember, you always put the conjugate base on top. Always put the weak acid on bottom. So pH is now going to be 7.2. Did I do that right? 0.15. Why did my pH go up a little bit? 7.21 plus the log of 0.105 divided by 0.095. It says that my pH is 7.25. Let me check. Let me double check. 0.08 plus 0.015. 0.12 minus 0.015, 0.105. 7 point, did y'all get the same thing? Plus the
Yes.
log.
Didn't it go down because on the first part this says the pH is 7.39, wasn't it?
Oh, yeah. Sorry, I'm looking at my pH. Thank you, Danielle. I was like, why did it go down? I'm not comparing it to the pK. I'm comparing it to 7.39. So it did go down. Okay. I was clearly I've been doing this for a minute. Okay. So pH went down a little bit, but not much. It held it relatively constant. Okay, now what happens when you add a strong base? We need to wrap it up because we're 15 minutes over. Strong base, let's say we just add 0.02 moles of NaOH. And now I have 800 milliliters of buffer. All right, real quick, we're gonna do this. And then if anybody has time to stick around for a quick functional group problem, we'll look at that. Same thing here. First thing I'm gonna do is calculate molarity of NaOH, which is 0.02 moles divided by 0.8 liters. 800 milliliters is 0.8 liters. So I'm just making up numbers here, but this could all be valid stuff. 0.025 molar. That's my concentration. Now set up your ice chart. Calculate. Calculate how the concentrations of weak acid and conjugate base change. So your initial concentrations are always the same. What part A told you is that initially you had 0.08 molar and 0.12 molar. And then this is going to be opposite. So see your plus and your minus signs right here. It's going to be opposite. When you add base, you add to the base column. Okay. By the amount of the molarity of the base. All right, those are your new concentrations. Now you plug this into Henderson-Hasselbalch. So pH equals pK, which is the same as before, 7.21, because we have the same weak acid buffer component, plus the log of, now you plug in 0.145. Always put the conjugate base on top, concentration, and 0.055 of the weak acid on bottom. So your equation becomes 7.21 plus the log of 0.145 divided by 0.055. My new pH, once I neutralize all of that base, is 7.63. So it raised it from 7 point, initially we had 7.39. When you add some of the acid, the buffer neutralizes it. The new pH is 7.25, lowers just by a little bit. When you add strong base, the buffer neutralizes it, but the pH is raised just by a little bit. Okay, questions on a buffer problem. Bailey, how do you feel? These are hard. Okay, good. All right, really quick. Functional groups, and then we're done. I've about hit my limit. So I'm going to go to the electronic textbook, and I'm going to go to chapter 12. And there's a problem on there. I'm just going to share my screen. Thanks for joining and hanging around. If you got to go, I totally understand. This is the last problem I'm going to do. All right, chapter 12. Man, my computer is slow today. Here we are. Additional section problems. Here it is. So let me share it to the desktop. Okay, you guys can see this. Catherine said, will there only be one problem we have to send a pic of? Oh, like a file response question? Yeah. And guess which one it's going to be? I bet you can guess. Mm-hmm. Yep, a buffer problem. All right, look here. It says identify identify the highlighted functional groups in the following molecules. Okay. So I only ask you to memorize 11 of those, and they're on the video. So I'm actually going to pull that up. Functional groups. There it is. Did y'all like my hike? All right. So aromatics. So if you see something that looks like this in the structure, you just call it an aromatic. Okay. It's giving you an example of benzene, but you don't. It's not benzene. Just an example. The name of the group is aromatic. Now, functional groups are recognized structures or portions of molecules, and their behavior is the same. So it helps us determine how chemical molecules behave in the body or in reactions because they're always predictable. So others, alkyl halides. So anytime you have a carbon bonded to a halogen, so for example, you would have this carbon here. Anytime you see like a chlorine, fluorine, bromine, iodine, that's an alkyl halide. Alcohol is an OH group. Okay. So anytime you see a carbon bonded to an OH group, you call that an alcohol. An ether is a carbon-oxygen-carbon combination. So you see this oxygen single bonded to two carbons, that's an ether. An amine is a carbon-nitrogen. A thiol is a carbon bonded to a sulfur, SH group. Okay, so anytime you see these in portions of molecules like this over here, these line structures, you're going to name it alkyl halide, alcohol, ether, amine, thiol. So where it gets more complicated are when you have these carbonyl groups, okay, because each functional group has a carbon-oxygen double bond. So there's all different kinds of carbon-oxygen double bonds here. All right, so let's see. Here's where I give you some practice and I'll walk through different examples and I say, okay, what's that? That's an amine. What's that? It's a carboxylic acid. All right, so let's see if we can name some of these on this. All right, NH. Okay, an NH group, the one highlighted in blue here. NH, anytime you have a carbon single bonded to NH, that is an amine group. Okay, so you would literally, probably I'll give you a structure that looks like this on the exam and I'll have each group labeled number 1, number 2, number 3. So we'd say group 1 here is an amine group. That makes sense? And you'll have your slides or your notes for this functional group stuff. The lecture slides are on Blackboard, so just download them or have them visible. That is an amine. Okay, anytime you have a carbon double bonded to an oxygen and then next door you have a nitrogen, you just scroll up and find, okay, where's my carbon oxygen double bond? It looks just like this. You got a carbon oxygen double bond and then the next door it's got a nitrogen. It doesn't matter if that nitrogen is bonded to a hydrogen or two hydrogens. You just have this right here. That is called an amide, A-M-I-D-E. And you see how that looks like this right here? Carbon oxygen double bond and next door is a nitrogen. That's an amide. Okay. Okay, what about this? Group 3, a carbon-oxygen double bond, and next door is an oxygen. Well, let's go see what that looks like. I actually don't think I asked you to memorize this one, so I won't put anything like that on the exam, but that's an ester. Okay, carbon-oxygen double bond, next door you have an oxygen single bond. That is an ester, but I'm not going to ask you about esters. Okay, what about a carbon-oxygen double bond with an oxygen or a hydrogen? That carbon is bonded to a oxygen and a hydrogen. Double bond to the oxygen. Sorry, I zoomed way in. I did not mean to do that. Oh gosh. So I don't know. Sorry, I'm trying to get out of this. Okay, there's the X. This is a, let's look at our slides. It's right here. It's called an aldehyde. Carbon oxygen double bond, single bonded to a hydrogen. So this is just this is an example of what I'm gonna have you do on the exam. And then look right here. What is this group right here on part B? That's the first one we talked about. It's an aromatic. Okay. So you'll have to look at groups. This right here, a carbon single bonded to an OH group, that's an alcohol. Here you got a carbon double bonded to an oxygen, and then you got an OH group, that's a carboxylic acid. We actually talked about that early on in chapter 10, carboxylic acid. That would be an acidic hydrogen. So there's examples. Some of these